What's up, AP Physics C Mechanics student? Welcome back to our elegant physics videos. Today's topic, 5.6, Newton's second law in rotational form, part 1. So let's jump right in. A massive pulley of mass m and inertia I pivoted from its center is being acted by two balanced forces F1 and F2. And if we assume that the radius of this pulley is given by 0.1 meter, then one can calculate the torque produced by F1 and F2. Remember that the torque equals F times D times cosine theta, where theta is the angle between the tangential direction and the line of action of the force. For simplicity, we're going to assume that these two forces are acting tangentially, which makes the theta equals to 0 and the cosine theta equals to 1. So no need to worry about the cosine. We just need to evaluate the force and the distance. Now, the distance is defined to be the distance between the point of application of the force and the pivot point. So the magnitude of the torque produced by each force, and this is the magnitude, tau is equal Fr, the force is 20, the distance is 0.1, which associated with the radius, and it's equal to 2 Newton dot meter. Now, since they are acting in opposite direction, the rotational effect of this force in this way, and for this force in that way, if we consider the positive sense in the clockwise direction, then one of the torques will be positive, the other torque is negative, and we will have, as a result, balanced torques. The pulley will preserve its state of motion either at rest or uniform motion. Suppose the right force is increased, producing more torque. Now we have increased the F1 from 20 Newton to 30 Newton, which makes the torque produced by F1 much higher. So we recalculate the torque for F1 and we will find that the torque is 3.5 Newton dot meter minus 2 Newton dot meter. The torque due F2 remain the same, and we'll find that the difference is equal 1.5 Newton dot meter, which is not equals to 0. This increase will cause the pulley to accelerate clockwise by a net amount of 1.5 Newton dot meter. However, we cannot equate torque by acceleration, so we cannot assume this value as acceleration due to the fact that we have different unit here. Newton's second law of rotational states that unbalanced net torque cause a body to accelerate. The value of this acceleration is the ratio of the net torque and the inertia, and this can be written mathematically in this way: alpha, the angular acceleration, equals tau net over I. Or, in more general way, tau net is equal I times alpha, which is in complete analogy with F net is equal M times A. In the rotation, we have promoted the force into torque. The mass has been promoted into rotational inertia. The acceleration has promoted to angular acceleration alpha, and the F net equals MA is promoted now to tau net is equal I alpha. Now let's solve example 1. Calculate the angular and tangential acceleration of the pulley given that its mass is 1.25 kilogram and the radius is 0.1 meter. Also, as an additional given, we have the magnitude of each force and the rotational inertia of the disk, which is given by half mr squared. Now, before we implementing any law, we should state all the forces acting on the pulley. So the forces acting on the pulley are, let's use the rigid body diagram to represent all the forces acting on the pulley. Now, in addition to these two forces, F1 and F2, we have the force of gravity, and it's acted on the center of mass of the pulley, and the reaction at the pivot R, which is acting in the opposite way. Now let's apply Newton's second law for rotation. Tau net is equal I alpha. So torque due to the gravity, torque of reaction, torque of the first force, and the second force. However, the torque of gravity and torque due to the reaction are equals to 0, since in both cases, in both forces, the line of action of each one of these forces is passing through the pivot, and the pivot is located here, and they are passing through the pivot. So we just need to calculate the torque due the forces F1 and F2. Now for F1, since the two forces are acting tangentially, no need to worry about the sign. We know that the torque is equal, can be plus or minus force times distance. Consider the positive sense in this way. So this force has rotational effect in this direction. This is the clockwise direction, and we're going to use the positive sign for this torque. the force is F, and the distance represents the distance between the point of application of the force and the pivot, and this distance associated with R. So it's going to be Fr. The tau for the second force, since it's acting in the opposite way, it will have negative sign and Fr. So for F1, we have F1 times R. For F2, or for tau 2, is equal minus F2R. Now, since we are looking for the angular acceleration and the tangential acceleration, I decided to calculate the tangential acceleration first. You can find the angular acceleration first, it's fine. Now, to find the tangential acceleration, you just need to re-express alpha as A over R, due to the fact that the angular acceleration and tangential acceleration are related to each other via this formula. So alpha is equal A over R, so we just need to replace alpha with A over R, and this is what I did here. R with R cancelled out, and here we will have survived R. Now, if we took the R as a common factor from the left-hand side, we can cancel it with the R on the right-hand side. And finally, we'll get F1 minus F2 equals half MA. This is A and not alpha anymore, because we have replaced it. Now, to find the A, the acceleration, which is in meter per second squared, we just complete the isolation by moving half M to the other hand side. Substitute, and we will get the value of the acceleration, which is equal to 240 meter per second squared. Now, this is the tangential acceleration. To find the angular acceleration, we just refer back to the formula alpha equals A over R. So we just need to divide over R to get the angular acceleration. And the angular acceleration is 2,400 radian per second squared. Exercise 1. A wheel of mass m, which has a rotational inertia I and radius r, rotates with angular speed omega about an axis through its center. A retarding force F is applied tangentially to the rim of the wheel. Which of the following is equal to the magnitude of the angular acceleration of the wheel? Okay, so this is the wheel, and let's assume that the pivot is here. The applied force is acting tangentially in this direction, for example. The radius is r. Now, to find that the alpha, the angular acceleration, we just apply Newton's second law in rotational form, so the tau net over I. Now, tau net represent the net torque acting on the wheel. Now, here we have three forces acting on the wheel: the applied force, the gravity, and the reaction of the wheel. So let's call it F-axis. However, since these two forces are passing through the pivot point, so the torque of the gravity and the torque of the axis are equals to 0. So only we will have the torque of the force to worry about. Now, for the torque of the force, if we consider the positive sense to be in this way, the rotational effect of this force is going to be within the positive sense, which makes this torque to be positive. Now, the force with the magnitude F, the D is the distance between the point of application of the force and the pivot, and it's associated with R. No need to involve the cosine because it's tangential force. And the correct answer would be B. Now, exercise 2, given the graph above of angular acceleration versus time for rigid body rotating about a fixed axis, which segment of the graph represent the time interval during which the largest magnitude of the net torque is exerted on the rigid body? According to Newton's second law of rotation form, the tau net is equal I alpha. Since we are talking about the same body, then the rotational inertia remain the same. Especially, they didn't mention any variation in the rotational inertia, so this is constant. So in order to have the torque to be maximum, then the angular acceleration must be maximum. And the maximum value of the angular acceleration actually happened at A. At A, we have the maximum value of the angular acceleration. So the correct answer would be A. A solid disk of mass m and radius r and rotational inertia I is free to rotate about a fixed frictionless axis that is perpendicular to the disk through its center. As shown above, a force of constant direction and constant magnitude F is exerted on the disk. If the disk accelerates from rest, so omega 0 equals to 0, at time t0, through what angle does the disk rotate? So actually here they are asking us about the angular displacement, or the delta theta. Now, applying Newton's second law to calculate the alpha, the angular acceleration is equal tau net over I. Now, the tau net is given by the tau of the gravity plus the tau of the axis and the tau of the force. Knowing that we have three forces acting here: the force of the axis, the applied force, and the gravity. Or again, the tau of gravity equals to 0 because these two forces, the line of action of these two forces are passing through the pivot point. Now the tau of F is given by F times R. Using the previous argument, we can, in the previous exercise, you can get this expression F times R over I. Now the magnitude of the angular acceleration is given by Fr over I. And this value is constant because all the quantities here in this expression are constant. And since they are constant, then one can calculate the delta theta using the kinematics equation. So delta theta is equal omega 0 t plus half alpha t squared. We know that the object starts from rest, so omega 0 equals to 0, and the delta theta equals half. The alpha is given by Fr over I times t, and the final instant is capital T, so let's replace this t with capital T. So finally, the delta theta equals Fr t squared over 2I. So the correct answer is B. The bar shown above is pivoted about one end and is initially at rest in a vertical position. The bar is displaced slightly, and as it falls, it makes an angle theta with the vertical at any given time, as shown above. Which of the following graphs best represent the bar's angular acceleration alpha as a function of theta? Now, first, we need to find a relationship between alpha and theta before we evaluate the graphs. And we're gonna use Newton's second law in rotation form. So alpha is equal tau net over I. How many forces acting here on the bar? Actually, we have two forces. We have the gravity and the reaction of the axis. Now, since the axis, or the force of this force, F axis, is passing through the pivot, this is the pivot, then the rotational effect of this force is 0. So we just need to evaluate the tau of the gravity. Now, we know that from the Z shape, the angle here is theta, as well as the angle here is theta. So this angle here is theta. But in the torque formula, torque is equal F times D times cosine theta. The theta here is the angle between the tangential direction and the line of action of the force, which means this angle. Now, since we know this is theta, then this angle becomes pi over 2 minus theta. So tau is equal, the rotational effect here of this force is in this direction, which is the same as the positive sense if we consider the positive sense in this way. So we use the plus sign. The magnitude of this force is as m times g. The distance, if we consider the total length of the rod is L, then the distance between the point of application of this force and the pivot is L over 2. So this distance is L over 2. Times cosine the angle, and the angle between the tangential direction and the force is pi over 2 minus theta. But we know that pi over 2 minus theta can be written as sine of theta. Let's use it back in the formula, and the alpha equals mg L over 2 I sine of theta. The only variable in this equation is the theta. Here, this ratio, it's a constant. Since the mass is constant, the gravity is constant, the L/2 is constant, and the rotational inertia is constant, which make the alpha written in the form of sinusoidal function. And alpha is related directly to the sine of theta. We know that the sine of theta is drawn in this way. So just with the simple compare between this graph and the choices, we can realize that the correct answer would be D. Because we just need to focus on this part, which is exactly the part that we got from the sine graph. So it cannot be this one because it's concave up in this way. This is linear, this is linear, this is constant, and the alpha cannot be one of them since it's attached to the sine of theta. Okay, exercise 5, you can consider it as part B of the previous question. Remember that the alpha that we got, it was constant multiplied by sine of theta. Now the bar shown above is pivoted about one end and is initially at rest in vertical position. So it means omega 0 equals to 0. The bar is displaced slightly, and as it folds, it makes an angle theta with the vertical at any given time, as shown above. Which of the following graphs best represent the bar's angular velocity omega as a function of time? Now, since omega 0 equals to 0, then any graph that does not start from 0, we can eliminate it, such as B, such as D. So it cannot be B or D because they not start from the 0 velocity, angular velocity. Now, from the previous exercise, we have found that the alpha is equal constant times sine theta. We know that the theta, as the theta increases, the sine of theta increases. And if the sine of theta increases, then the alpha increases. So alpha is increasing. On the other hand side, omega with respect to time, the slope of this graph is represent the alpha, the angular acceleration, using the trick that the slope for the time graph, theta time graph, represent the omega, and the slope in the omega time graph represent alpha. So we need to look for omega time graph such that the slope of this graph, it should be increasing. Now it cannot be A because A, the slope in A is constant, neither increasing nor decreasing, so constant, so we cannot take A. Now C or B, to evaluate the slope, we just track or the tangent of a line at a different point, and you can realize that the slope is decreasing because it becomes less steep. For E, at different point, the steepness of the line is increasing. So here we can say that the slope increases. So since the slope represents the alpha, then alpha increases, which means E is the correct answer. So the correct answer is E. A solid disk of mass capital M and radius r is free to rotate about a fixed axis through its center. The rotational energy of the disk around its center is mr squared over 2. A force F is applied tangentially at a distance r over 2 from the disk, as shown in the figure above. What is the angular acceleration of the disk? So here again, we need to apply Newton's second law of rotation form. Alpha is equal to tau net over I. Now, how many forces acting here? We have the tangential force, we have the reaction from the axis, and the gravity. However, these two forces has no torque because the line of action of these two forces is passing through the pivot. So the rotational effect due to these two forces will be cancelled. So we just need to evaluate the torque of the force F. Now, since here all the values are written in the absolute value, no need to worry about the sign. We just need to evaluate the magnitude of the alpha and the magnitude of the tau F. Now in magnitude, we just write F times D. What about the cosine? This is tangential force, no need to write the cosine. Now the distance represents the distance between the point of application of the force and the pivot, and the distance here is r over 2. So we write of F r over 2 over I, and the I is given by mr squared over 2. Now half with half cancelled out, so F over mr squared, which means sorry, and r will be cancelled with 1r, so F over mr, which means the correct answer is C. A wheel with a rotational inertia I is mounted on a fixed frictionless axle. A wheel with rotational inertia I is mounted on a fixed frictionless axle. The angular speed omega of the wheel is increased from 0 to omega final. In time interval capital T, what is the average net torque on the wheel during this interval? In general, the tau net is equal I alpha. If we are looking for the tau net average, we should consider the alpha average. And we know that the alpha average is given by omega final minus omega initial over time. Omega final minus 0. The final angular speed is omega final. The initial omega is 0 over the time interval, which is given by capital T. Now use it back again to in the formula, and we will get that the answer is I multiplied by omega final over capital T, which makes E the correct answer. A solid cylinder of mass m and radius capital R has a string wound around it. A person holding the string pulls it vertically upward as shown above, such that the cylinder is suspended in mid-air for a brief time interval delta t, and its center of mass does not move. And this is really important. We will see later that it allows us to apply the translational equilibrium for this interval of time, since the center of mass of this wheel does not move during this time. The tension in the string is T, and the rotational inertia of the cylinder is about its axis is half mr squared. The linear acceleration of the person's hand during the time interval delta t is. So during the stationary translational motion of the mass, we need to find the acceleration, the linear acceleration of the hand. Now the linear acceleration of the hand is the same as the linear acceleration of the string. And the linear acceleration of the string is related to the angular acceleration of the wheel via this formula. A is equal R times alpha. So if we know what is alpha, we can find A. Now tau net equals I times alpha. Since we are interested in A and not alpha, we can do the change, such as alpha can be expressed as A over R. So we can write I A over R. Now how many forces acting here? We have the gravity and we have the tension. So only two forces acting here and no force from the axis, because it's not fixed with an axis. Now we know that the torque due to the force of gravity is 0 because this force is passing through the pivot. We just need to worry about the tension, the torque due to the tension. Now the torque due to the tension, we're going to consider this time the positive direction to be in this way, because again, most of the expressions are given in the absolute value, and which makes the rotational effect of this force to be positive within the direction of the positive sense. So we write plus the tension force multiplied by the distance between the point of application and the pivot, which is equal to I A over R. Now, R can be, we can multiply both sides with R, and we will get I A R squared. Now also I is given here with half mr squared. Now r squared with r squared cancelled out, so the acceleration now is 2t over mass. However, none of these choices contains my answer, which means we're going to use the translational equilibrium to complete the solution. In the translational equilibrium, the tension equals to the force of gravity, so we can replace the tension with the force of gravity. So 2 times mass times gravity over mass, with mass cancelled out, and the final answer would be 2g, so the correct answer is B. Now, exercise 9, a disk initially at rest is acted upon by a constant net torque tau. The disk spins for a period of time t and rotates an angular distance delta theta. So in the first trial, when we applied this net torque, we got this delta theta for this amount of time or period of time. The same disk is brought to rest. Now in the second trial, we started from rest again. The disk is now acted upon by constant torque 2 tau. So we have increased the torque by 2. The disk spins for the same period of time. What will be the new angular distance, the new delta theta of the disk? So here we're gonna apply the factor of change, but in order to apply the factor of change, let's construct an equation that can be used to find the delta theta. We know that the delta theta equals omega 0 t plus half alpha t squared. In this form, we cannot apply factor of change because it involves plus. So, however, this part can be cancelled because we have started from rest, and delta theta equals half alpha t squared. Now, alpha itself is not mentioned in the question, but we can write or re-express it in terms of tau because alpha is equal tau net over I. So we just need to write half tau net over I times t squared. Now let's apply the factor of change. Now the half, it's a constant. We replace the constant by 1. The tau net, in the second trial, we have increased the tau net by 2. The moment of inertia, we are using the same disk, and the disk is spinning around the same pivot, so the rotational inertia will remain the same for the same time period, which makes the final factor would be 2. And the correct answer is D. And that's it for today's lesson on 5.6 Newton's second law in rotational motion part 1. Thank you for joining me. See you next time.